Okay, let's go ahead and get started. It's time for class to begin, so let me turn down the lights a little bit. Feel free to have a donut. Whoever gets here first gets first choice. You're welcome. All right. So last time we learned about the question, what is truth? And we learned about propositional logic. So last time we learned about what is truth, and we learned about propositional logic. This time, we're going to learn about something called truth tables. All right, so this time we are learning about something called truth tables. So just as a review, can anybody tell me the 5 logical operators that we learned last time? So what are the 5 logical operators that we learned last time? Okay, and let's put them in order of the precedence. So there was not, you're right, yep, that's right. There was the operator called not. And then there's the operator called and, an operator called or, implies, and if and only if, right, exactly. And then there was exclusive or. That's not really one of the 5. That's just kind of like another type of or in parentheses. This is called exclusive or. And we also learned that if and only if basically is just like saying something equals something. Remember? Because if it's if and only if, it has to be, it's only true if both of them are equal to each other. So this basically just means equals, and the exclusive or basically just means not equals. When it's applied to a true or false value. That means not equal to, that the other one means equal to. So those are the 5 logical operators we've learned. Now let's learn some propositional logic. So first of all, let's just start with the proposition called P. So P is a proposition. Now let's give the full possible list of values for the all values it can have tabulated together are called the truth table. Are a truth table. So if you just have the letter P, the list of values that it can have is it could be true or it could be false, right? So that's the truth table for the proposition P. Let's see if we can get a little bit more complicated though. So what's the first logical operator we could apply to P? It would be not P, right? So if we apply the logical operator not P to P, what's the opposite of true? What is not true equal to? False, correct. And what is not false equal to? True. True. So the values that not P would have corresponding to the values of P being true and false would be false and true. And sometimes they call this a logic circuit. So there's like circuits in a computer working together, like AND gates and OR gates and stuff like that work together to like the input values are like true and false, and then the output value is like false and true. So like that would be a NOT gate. Let's go ahead and let's try to add on some more things to that actually. So let me erase that a little bit. So are there any other logical operators that we could apply to just the letter P? Or not? Well, all the other logical operators have to have at least two sides to them, right? So that's probably about all that we can do to the value P. So now let's have P and Q. So let's make a truth table just simply of P and Q. So the P and Q truth table is a truth table that contains all values tabulated together that P and Q can have. So Now, the way it works like this is if there's one logical value, it can have two answers, a true or a false. Now, if you add two together, though, there's twice as many options, though. So what's 2 times 2? 4. Right, exactly. So there's actually, for P, we are not allowed to just put down true and false this time. We need to put down a total of 4 options. It needs twice as many trues and twice as many falses. Why is that? Because for each value of P, there needs to be every possible value of Q. So if P is true, Q could be true or false. And if P is false, Q could also be true or false. So it's just like going to a restaurant and picking how many different toppings you want. If they have, let's say, cheese and bacon, you could get it with cheese and with bacon. True, you could go true for both bacon and cheese. Or you could get it with cheese but without bacon, which would be true and false. Or you could get it without cheese and with bacon, which would be false and true. Or you could get it without bacon and without cheese. I said that in the wrong order, but without cheese and without bacon, and then it'd be false and false. So those are all the possible truth and false values that P and Q could have in combination with each other. But now though, once we have that, we could also use some logical operators that operate on 2 things at once instead of just one. So let's go ahead and add some more columns to this. Now you can add as many columns as you want to, as much as you feel a desire to do. So let's just do the AND operator. So let's do P and Q. Remember, P and Q means that you have to have both in order to be allowed to get in or whatever. So both of them have to be true in order to be allowed to be true. So what is the truth value of true and true? It's true as well. What's the truth value of true and false? So P and Q, P represents in the next row, P represents true and false, and P represents true and Q represents false. So what's the truth value of true and false? False, correct. Good job. And what's the truth value of false and true? It's false. What's the truth value of false and false? Okay, that's not quite right. That's all right. Okay. So, by the way, let me go ahead and do attendance again. I'm going to do attendance again. I saw some new faces. If you weren't here right when I first began, raise your hand. Okay, so what's your name?
Zoe.
Zoe, perfect. Excellent job. And then who else raised your hand? What's your name? Amani, perfect. And who else raised your hand? What's your name? Keep quiet. Abduro. Funny on the list. Arturo. Arturo? Is that right? Okay, Arturo. Perfect. And what's your name? Were you here already? Yeah.
I showed like 3 minutes.
Okay, what was your name? Did I get you on? What? Isaac. Okay, Isaac Garza. Okay. So let me just read off the names that I haven't called yet. Okay, let's see. Anthony. Are you here, Anthony? How about Noah? Are you here, Noah? How about another Anthony? Is there any Anthony's here? Taylor. Taylor, are you here? Okay. That's too bad. Okay, so I guess there's 3 people missing.
Yeah, there was like a huge crash on Kellogg. So
Oh yeah, okay, that's too bad.
Yeah.
That's all right. Okay, so now let's go ahead and see what else we could do. So what's the next logical operator after the AND operator? I know this is getting boring, but this is going to get complicated really soon, though. It's going to be like OR, yep. It's going to get complicated pretty soon, so make sure you're paying really close attention. So if P, now remember when we talked about OR, this is like the OR that means you can have one thing or the other to be able to be allowed in the building or whatever. So if you have P or Q, if it's true or true, that comes out to be allowed, right? Because if you have both credentials, they're still let in it. Like they wouldn't not let you in. if you had even more than you needed, right? So what about if you had P? So what if you had P and Q was true and false? I'm not true and false, true or false. Would you be allowed in if you had one thing true and the other one false, but you only needed to have one or the other? Yes, you would be allowed, so that would be a true. And what if you had false and true? I mean, sorry, false or true. What would that be allowed? False or true? That would be true. That would be allowed. What about false or false? What if you went up to like let's say the Olympics to like take pictures or something, and you had like a little fake like thing that said like, hello, this is from first grade, like another little fake thing, would they let you go in the security gate? No, you wouldn't be allowed. They'd say false for that. So if everything's false, then it comes up false. So P or Q works out to be true, 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 false. So this has more truths in it and only one false. This has only more falses in it and only one thing that's true, right? Now let's go ahead to the next logical operator. What comes next after and or? Implies, correct. So P implies Q. So what does P implies Q mean? So remember I said, think about it meaning like that you were having a birthday in a week, and so you told your friend that you would work for them now. No, I'm sorry, you made a deal with your friend that they would work for you on your birthday if you worked for them today or like tomorrow or like an extra shift for them beforehand. So P is like you're gonna work for them now, and if you work for them now, then they'll work for you on your birthday, right? That's what it basically means. So that means that P implies Q, or it really means, you could also say it means if P, then Q. That's the way it sounds in English. If P, then Q. So P arrow Q means if P, then Q. So let's think through this situation. So let's look at P. So P is true. So that means that I did work for you ahead of time. And then Q is true as well. That means my friend did work for me on my birthday. So if we both did it, did we keep our promises or not? Yeah, so that's true. So that is a true statement. How about this? If I worked for my friend on his extra shift for free or whatever, and then on my birthday came, he didn't work for me, did he keep his promise? No, he did not. So that's false. Then what about the next one? If I did not work for my friend on his shift, if I didn't keep his promise, but he still worked for me on my birthday anyway. Now, this is really mainly talking about the promise that whether my friend keeps his end of the deal or whatever. So, because because I'm really trying to get off on my birthday. So if I didn't even do it, but my friend did do it though anyway, did I still get to have my birthday off? Well, I did, because if he worked for me on my birthday, then it still worked out. So this isn't really nice, but it's still true because my friend worked for me, even though I didn't really work for him. So I didn't keep my part of the bargain, but the statement that I got my work done, my shift covered or whatever on my birthday still happened. So so basically from the company's viewpoint, it all happened fine because my friend basically had to work both times, but and I got to have my birthday off or whatever. So this actually comes out to be true. This is true, but I'm gonna say but not nice though. But not nice of me or whatever. So then how about the false on the last one? If I did not work for my friend today, and therefore my friend didn't work for me on my birthday, that he didn't actually break his promise though. So he still didn't break his promise. So this is actually still true. He didn't violate the contract because I invalidated the contract because I didn't actually work for my part. Good morning, by the way. I heard there was a big crash on Kellogg, is that right?
Yeah.
Wow. Okay. And you're Taylor, is that right?
Yes.
Okay, perfect. So thank you for coming. And by the way, have a donut if you feel hungry. There's that. So basically, this is the truth value of it. So there's really only one time it comes out to be false. What's the one and only time that an implication or implied statement comes out to be false? When somebody,
What's not true?
yeah, when the first person actually did their commitment and they did it, and the other person doesn't follow through with their promise. If the first person didn't follow through with their promise, then the second person doesn't have to follow through with their promise. So in the last part, it still comes up to the promise is still kept because when I didn't work the first time for my friend, then my friend doesn't need to work for me on my birthday anymore. Because I already basically canceled out his commitment. So the contract is still true. In all three other cases, the only time the contract has been broken is if this person did their part and the other person lied and never followed through. How does that sound? Like if you made a contract to somebody and said, if I mow your lawn, you'll pay me. If you did mow the lawn and they did not pay you, then the contract is broken. But if you did not mow their lawn and they didn't pay you, then the contract is not broken. Does that make sense? So it's only when the person does it, the other person doesn't come through with their part of the bargain, that it gets broken. So I'm going to erase the part that says not nice because in math, it doesn't matter if it's nice or not. It just matters if it's true or not. So there we go. Could we reverse it though? What if we said Q arrow P? How would that work? What do you think the truth and false values for Q arrow P would be? Let's use your critical thinking skills and try to tell me what they would be. So Q arrow P means that Q is agreeing to work first. And if they work first, then that person needs to fill in a shift for them later. So if Q works first and that person fills in a shift for them later, Q then P, that's a true statement, right? And then if Q comes first, if Q actually said they would work for a shift, but they didn't do it, and this person still does another shift later anyway, they're not breaking the contract, they're just being extra nice. So that's still true. If Q is supposed to work first and then P is supposed to work for them later on, well, here's Q, they worked first and then P did not work for them later on. That's when the contract is actually broken because the person did their part of it and the other person did not do their promise. And the last part, false, false, that's like saying that if you said you'd mow the yard, then you get paid. Well, if you didn't mow the yard, then you don't have to get paid. So if you did not fill in your shift first, the other person did not need to do their shift later. So Q implies P is true if actually neither one of them did either one of them. So once again, there's only one false value. Like that. So let me ask you a question. This is really going to require your biggest critical thinking skills. Is there any way to get those same values by using a different logical set of operations? Notice that the two columns have one true and three falses. One of them has three truths and one false. Is there any way to use an and or an or and a not or something else like that to get those same things? What would you say? Or? Yeah, we could use maybe an or. That's right, we could use an or, but none of the ors has the F in exactly the right place, right? So let's try something. Let's go ahead and add on to this truth table. I'm kind of running out of space, but let's try to add on a not. Let's try to calculate something so that we could use an or. You're right, an or has one false value, just like these. So the false value from an or, so this is where you get abstract. We're no longer thinking about what things actually necessarily mean, like friends, like somebody working for a job, somebody doing also. We're just looking at the shapes of the data, basically. So here we have all this stuff. We have an F right here. That F came from the spot where you had two falses in a row, right? So if I have P and Q, how could I make you get two falses in a row that would be in that spot instead of in that spot? So how could I make this true become false? How could I make the true, that the one that I circled, How can I make the true that I circled become a false? So that's the true that I circled a while ago. How can I make that true become false? By doing a what? No, there's a simple operation to just make that true become a false. It's not one that involves two operators, it's just a single operator. That's the not, right? So let's go ahead and do a not P, not P. If I do a not P, what's the opposite of true?
False.
So remember, P is true at first. Not P is false. Not true is false. Not false is true. Not false is also true. So that's the result of not P. Now, if I do, and now let's look down carefully at this. So there's not P, false, false, true, true. And then which one could I combine this with so that I could use an or, and I'd come up with this? I'm looking for true, false, true, true. I'm looking for this one. Let me circle it. So I'm looking for that. What operation could I put together with that so that I would get, sorry, what operation could I put together with Q so I get this? This is what I want to get. I could use an or, right? Not Q. So let's see here. So if I take, let me erase this red circle real quick. My fault. I say red circle. So if I take this false and this true, I would get a true, right? Take this false and this false, I would get a false, right? If I take this true and this true, I get a true. If I take this true and this false, I get a true, right? So let's put that in the truth table. Let's take the two circled red columns. Let's just see here. Q or not P, right? Q or not P. Let's write those down. What's the truth value of Q or not P? So here's Q, true, and here's not P, false. What's the truth value of Q or not P? It's what?
True.
True, correct. And what's the truth value of Q or not P in the next column? False, right? What's the truth value of true or true? And what's the truth value of false or true? Correct. So therefore, does P implies Q equal Q or not P? It does, right? P implies Q always equals the other one. So let me circle that in green. So this is an example of the study of logic. You can actually prove by looking, whenever you get two columns that are the same, those things are equivalent to each other. Therefore, P implies Q is equal to Q or not P. So that's just something a lot of people don't even actually know. But P implies Q can also be written in a totally different way. Now, which is easier to understand? If I said to somebody, hey, you work for me on my birthday, or I won't work for you now. Would that make sense? If I said you work for me on my birthday, or I won't work for you now, would that make sense? It wouldn't really make sense in English, right? But if I said, if I work for you now, then will you work for me on my birthday? That would make sense, right? Now, technically, logically, it means the same thing because they come out to the same outcome, right? But one sounds like really threatening and mean. The other one sounds nice and like friendly. Does that make sense? So now it might be more efficient for a computer maybe to just think about it like this. Either this bit is true or this bit is not true. Then it can calculate that answer. So we've kind of reduced it from a more human type meaning to just a more cold logical type meaning. But that's important to be able to do, is to see which things are logically equivalent to each other. So we've just figured out that P implies Q is equal to Q or not P. Is there another way of writing this? Now, by the way, the equal sign in math, they're a little bit mean. Equals can be generalized to mean more than just like 3 equals 3. They don't usually use the equal sign to equate things that are not numbers equal to each other. So this is really exactly a number. Like if you're in computer programming, you probably know that there's different data types, like there's Boolean data types for true and falses, but you could also store that as a bit, like a 0 or 1. So you could say it's a number, or you could say it's a true and false value. Now, if you think about the type of data, you probably wouldn't normally use an equal sign. You could, of course, but so P implies Q equals Q implies P. Is there another symbol we could use that I said means the same as equals? Yeah, so P implies Q is if and only if, which means equivalent to Q or not P. Right, correct. So P implies Q is if and only if Q and not P. There's also other things that are equivalent to them as well. So I'm going to take a little bit of a moment for you to take a deep breath and stop, look through that table, see if you have any questions about it. If there's any columns in it that didn't make sense, just let me know. Don't feel free to, you will not sound stupid or anything if you ask a question. There's one of those columns that did not make sense. Like look through the and column, this and this, make sure that makes sense to you, make sure the or column makes sense to you, make sure the implies column makes sense. Let me know if anything doesn't make sense, and then if everything does make sense, then I'm going to go back and I'm going to make erase maybe three of the columns and then fill them in with something different.
Right, shut off right now, right? So that's the last 2 columns.
Last 2. Okay, so first of all, the not P column is actually similar to the not P column up there. So just tell your brain to like skip over all the stuff in the middle. Just look at P. So just look at P and just put the opposite of P. So false, false, true, true. That's how I got the not P. And then how I got the Q or not P, you have to like, I think it helps if you take like your 2 fingers or 2 hands or whatever, put them on your page and like to keep them focused on where you're looking. So Q and not P, and it really means you're looking at Q together with not P. Put your hands on that, on those rows, and then say true or false. That's true, right? False or false, that's false. True or false, that's true. False or true, that's true.
Okay, I see.
Yeah. Yeah, so sometimes it helps if you just use your like actual hands to like keep your focus on only the 2 columns that are being operated on. Okay, well, there's that. Let's do, okay, so does anybody else have any other questions? If not, then I'm going to erase some of that. And we're going to talk about something called, we actually talked about it last time. Do you remember I mentioned the word converse? What did I say the converse was?
Keep the sign facing the same way, switch the.
Yep, you switch the letters. It's like switching the shoes to the opposite feet, like Converse tennis shoes, basically. So if I, let me change back to like, I'll change to black, I guess. So if I switch the letters to the opposite, wait, did I already do that? Did I already do a Q implies P that I just erased?
Yeah.
Wow, okay, I guess I didn't even think about that. So, okay, wow. Okay, so I guess I didn't mean to erase it. So now I'm going to talk about why was a Q implies P? Why was it not the same as P implies Q? Like, for example, if I say every dog has hair, isn't that the same thing as saying everything with hair is a dog? Is that true or not true? Well, am I a dog? I hope not. So it's not true if you reverse if you switch the letters in an implication statement, that is not equivalent. That's not the same meaning as the original one, right? Obviously, you can tell the P implies Q and Q implies P is not the same in every case. In 2 cases, it is the same. This is still the same, and that's still the same. But the other 50% of the time, it's not the same, right? So if you say P implies Q, or if you say Q implies P, they're not always the same. Just like it's not always the same if you say if you have all dogs have hair, and if you have hair, you're a dog, that's not really the same. It is true for everything that doesn't have hair, right? Because that's still valid for that. And it's also true for everything that's a dog, but it's not true for anything that's a mix of having hair but not a dog, right? So that's called the That's called the converse. Oops, I keep leaving my eraser on, sorry, accident. So we've already talked about that before. Converse of P implies Q is Q implies P. Now we're gonna learn something called the inverse. So what's the inverse? So what does it mean if you invert something? You invert the truth of it, basically. Well, not the truth of it. You invert the truth of the things being plugged into it. So that, let me change the word converse to be, hold on. Okay, do you have that written down? Okay, let me circle that actually. So there's the converse of it. And also, what's the inverse of, what is the inverse of P implies Q? It would be not P implies not Q. So is the inverse of something true or not? So in other words, if I say, if you're a dog, you have hair. If you're a dog, you have hair. Let's think. If you're, let me think of something else. If you're happy, no, let's say if you're on vacation, you're happy. Would that make sense? If you're on vacation, you're happy. That would be a valid implication, right? I mean, that's not valid, but I mean, it could be true, right? If you're on vacation, then you're happy. So is it true to say that if you're not on vacation, then you're not happy? It's not necessarily always true because you could be like on your wedding day or something else. You could be doing something else that's not your vacation, but still is happy, right? So the inverse of a true statement is not necessarily always true. So the inverse is not equivalent to the original. So let's do a diagram of the inverse. So let's do it. Hold on. Is it okay if I start a new page? I'm going to start a new page because there's too much on this page. So let's start another truth table, P and Q. So here's P. We need two of them. We need two falses as well. And here's Q, false, false, and true, true. So that's just a review. But this time we're going to need not P. And not P would be false, false. And hold on just a second. Somebody tried to call me, and whenever people call me, it always disables the audio, so I don't think any. Okay, perfect. All right, now back to connected to audio again. So not P is false, false, and then true, true. And not Q would be true, true, and false, false, right? So there's not P, not Q. Now, when we know both of those, now we can try the statement not P implies not Q. So not P implies not Q. Remember that, let me get this. There used to be this nice yardstick that I could use that was easier than using my hands, but maybe it's back here. Okay, so remember, we're looking at not P and then implies not Q. So if you did not mow the yard and the person you were supposed to mow the yard for still paid you money anyway, they did not break their promise, right? They were just extra nice. So that would not be breaking their promise to pay you. If you did not mow the yard and they still paid you anyway, that would still not be breaking your promise, right? Wait, did I do something wrong? Oh, I did something wrong.
The two middle ones on Q are supposed to be flipped.
Yeah, you're right, because you're right. My fault. I was like, why are the same things happening again and again? Okay, see the Q, when you do a truth table, you're not supposed to list just the opposites of P for Q. You're supposed to list every possible combination of toppings, just like you could get you could get cheese and bacon, or you could get cheese but not bacon, right? You could get you could get not cheese but bacon, or you could get not cheese and not bacon, right? So those are actually supposed to be like that. Okay, yeah, sorry. But by the way, feel free to raise my hand if you notice me like rushing through something and missing something like that. So Q is actually to make all combinations of truth that are possible, which a truth table is defined as all combinations of possible truth and false values for whatever you're given on the table. So it's either true, 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 false, or false, true, or false, false. Now we're ready to go ahead to the next part of the truth table. So not P would be false, false, true, true. And then what would not Q be? What would not Q be? So, false, true, right. Okay, now we're ready for the next step. So we're thinking about this is like a contract that says, if I mow the yard for you, then you have to pay me for it. So if I do not mow the yard, actually, then they do not need to pay me for it, right? So the contract has not been broken. It's still a true contract, even if nobody actually did it. Because if you didn't mow the yard, then the other person doesn't have to pay for it. Now, if you did not mow the yard and they still paid you for it, they did not break the contract. Well, I guess you broke the contract, but in terms of whether they broke the contract, they did. So how about true and false? If you mowed the yard and they did not pay you for it, then the contract is broken, right? And then how about the last one? True and true. That's the normal case. That's just both people kept the contract, so it's been kept. So true, true, false, true. So there we go. So that's done. So that's the truth value of the that's the truth value of the inverse. That's what the inverse state. Now let's go ahead and let's do one more on this table. That's called the contrapositive. Contrapositive is the biggest, baddest word of them all. It's bigger and longer than the converse is, and it's bigger and longer than the inverse is. That's because it's both of them at the same time. So the contrapositive is basically it's the converse of the inverse. The converse of the inverse. So, well, what is the converse of the inverse? What's the converse of the inverse? So there's the inverse. So let me write them down again. So there's the original, P implies Q. I'll say OG for original. That's what original means, right? Okay, so P implies Q, that's the original. Then we have the converse. What's the converse by itself? Q implies P, right? That's the converse. And then we have the inverse. What's the inverse of P implies Q? What's the inverse of P implies Q? Not P implies not Q. Yep, that's the inverse. And now what's the converse of the inverse? So remember, converse just means switching the shoes to the opposite feet. So if I switch this to this side, I would get not Q implies not P. Not Q implies not P. This is called the converse of the inverse, which is also called the contrapositive. So let's try to do the diagram for the contrapositive. The contrapositive is not Q implies not P. So basically, we're going to look at not Q. That represents the first thing that happens. This represents the second thing that happens. Not P. Wait, I think I didn't quite write the not P quite right. Sorry. There we go. So not Q implies not P. So now Q is actually, now it's like, let's say, have you ever heard a story of like somebody rich becomes poor and now the person who had the mansion is now the one mowing the yard? How about that? So now the Q person, that's the person who's mowing the yard, and this other person is the person who's supposed to pay them after they mow the yard. So if you did not mow the yard first and they didn't pay you for it later, then that's still true, right? So that would still come up to be true. True. And then if they, no, sorry, let me look at not Q first. So if you did mow the yard and they did not pay for it, that would be a false. That'd be breaking the contract. By the way, let me draw some lines through these so you can see it better. There we go. And then if you look at not Q, that implies not P. So if you did not mow the yard, but they still paid you for it anyway, because they remembered what it was like to be. No, you paid them anyway because I don't know why, but you wouldn't have broken the contract because you were just extra nice, right? Then if not Q comes first and not P comes last, so if they mowed the yard first and then you paid them afterwards, that's still true. So that's the diagram for not Q, then not P. So it's true, false, true, true. Now, who remembers the diagram from several minutes ago? Who remembers what the original diagram for the original was? What was the diagram for the very original statement P implies Q? What was that? It was the same. It was true, and then it was false, and then it was true, and then it was true, right? You're right. So the diagram for P implies Q actually works out to be the same as the diagram of a contrapositive. So contrapositive is actually another logical equivalent to the contrapositive. The contrapositive is actually equivalent to the original, to the P implies Q. So we already know now two things that are equivalent to P implies Q. What was the other thing that we knew that was equivalent to P implies Q?
P or Q.
Not P or Q, right? Not P, sorry, not P or Q. Did I say not P or Q, or did I say Q or not P? I'm not sure, but both of them are the equivalent anyway, but. Yeah, so we now know three things that are equivalent, and it's good to know multiple things that are equivalent to each other. So the very last thing we're going to learn today in the last 7 minutes is how to negate something that is more complicated than just one single thing. So we already know how to negate a single proposition by itself. Like, for example, what is the negation of true? It is false. So the negation of P is the opposite of P, right? But what's the negation of something that's more complicated? What is the negation of something that's more complicated than a single statement? So let me do, hold on, let's see. There we go. What is the negation? Negation of complex logical statements. All right, so what is the negation of? Well, a complex logical statement is something that has more than one thing involved in it, right? Complex means like multiple parts. So the first operator that has multiple parts in it is the AND operator. So what's the opposite of P and Q? So what's the negation of P and Q? The negation of P and Q is equal to, so think about this logically first. So if somebody said, I have a PhD in chemistry and I have a PhD in physics. That's what their claim is, right? Their claim is they have both. So there's multiple ways that they could have a false claim. What's one of the ways that their claim could be false? One way is they don't have anything, right? Another way it could be false is if they do have one, but they don't have the other one, right? So basically, it could be that they don't have both, either one or the other, or it could be that they just don't have one or that they don't have the other. Well, we've learned in math that the logical word or implies that they either don't have one or they don't have the other, or they don't have both, right? So the negation of this is that they either don't have one or they don't have the other, which implies, or they could also don't have both. But you don't have to say, or they don't have both, because in math, the implication that you could, that one or the other means that you could also have both. That's just automatically implied. The only time that does not automatically imply that you could have both things in an or statement is the exclusive or, which means that you only have one or the other, but you do not have both at the same time. So then this is pretty easy to remember, actually, if you think about it like this. Now, this isn't really logical, but think about it like multiplying. The negation of a p is not p. The negation, now this isn't really true exactly, but the negation of this symbol, you could think about it like this, is it flips it over. Then you negate that one and it just negates that one. So basically, if you just flip everything, it actually works out. All right, now what's the negation of, what's the next operator besides and, after and? It is or, right? So what's the negation of an or? Well, it actually works the same way. So the negation of one thing or another thing is not one and not the other one. Perfect. Good job. And what do you think the negation of an implication is? This is where it gets a little tricky. What's the negation of an implication? What's the negation of P implies Q? So we could do it directly by thinking about logic a little bit. When's the only time that that contract would be broken? We learned about this maybe 3 different times when we diagrammed it. When's the only time that you're actually technically breaking the contract if you say P in the present implies Q in the future? That would only be broken if, what? You mowed the yard and they didn't pay for it, right? That's the only time it's actually broken. So this only time this is actually negated is if P is true and they did not pay for it. And another way of remembering this, another way of proving this is that you could say, since another way to negate P implies Q is just to remember that P implies Q is equivalent to saying Q or not P, right? And so since we already have talked about this, we know that P implies Q is actually the same as saying Q or not P, right? I think that's what we said, right? Now, what's the negation of Q? What's the negation of an or? If I distribute the negation symbol to the Q, I would get not Q. And if I distribute the negation symbol to the or, I get an and. If I distribute it to the not P, I get a P. And so I get not Q and P. However, though, if you say the or operation is commutative, which means A or B is the same as B or A. So if I just switch this around, I get, sorry, I meant to say the and operation is commutative. A or B is the same as B. A and B is the same as B and A. So we get P and not Q either way. So basically, we've just learned that the negation of an implication is P and not Q. And that's the end of class for today. So we're going to come back to class on Friday again, and I'm probably going to cut a little bit of the homework problems for you on the assignment. So you can go ahead and look at the homework assignment a little bit in Moodle, but don't actually do all of it yet though. You can think about it though. Get a head start maybe, but don't do all of it because I'm probably going to take some of the questions out and maybe I'll change it up a little bit. I'm probably maybe going to add in like maybe one more truth table to it as well. So I'm probably going to take some of it out and maybe add in one more truth table problem to it. Thank you very much and have a great day, everybody.
Set up another